Hi there. Let's deal with our first topic in our last chapter on light. And today we're going to talk about sources of light and how we might calculate different devices for how much energy they're using up. So, what is light? Well, most people would say light is a special kind of wave. And the word special is used because it's a bit of a mystery to scientists in regards to how light sometimes behaves. In many instances, it has properties that make it behave like a wave. However, there are some instances where light doesn't behave exactly like a wave, kind of like a rope, but like an individual particle of energy called a photon. So it kind of flip flops. So let's talk about that. So, what do we say? Well, in most cases, we as basic scientists treat light as a wave. However, as I said before, scientists also talk about light as a photon. So, let's look. Here's the electromagnetic spectrum, which is the different forms of radiation and energy. And according to that, objects that have radiation give off energy in the form of these invisible waves. And waves have crests, and the length between the two crests we call the wave length. And so light, when it behaves like a wave, goes in straight lines, and we can predict the direction and the pattern that happens when light travels like a wave. However, some objects emit light through photons. So, what is a photon? Well, here's a picture of an atom with the nucleus, and outside the nucleus, we have electrons. These electrons have different amounts of energy depending on whether they're closer to the nucleus or a little bit farther away. And some substances can have the following happen to them. A collision with some other particle hits the atom, and what that does is it causes an electron to jump up to a higher energy level. Then, when the particle goes back down to the lower energy level, a special particle of energy is given off called the light photon. And this is how some objects give off or emit light. So here's the electromagnetic spectrum. This is gamma rays, which are the strongest kind of radiation. Gamma rays have waves that have really short wavelengths. And X-rays, UV, visible light, which we can see with our eyes. So the different colors of the rainbow are different forms of light that have a certain wavelength that our eye is able to see. Infrared, we can't see with our own eyes. And then radio waves. So radio waves have long wavelengths, which mean the distance between the two crests is a long ways away. When it comes to light, objects are either luminous, which mean they can form energy that can be detected by our eye, or in other words, they give off light, or they're non-luminous, which means the only way we can see them is when light is reflected off those. So an example of a luminous object might be a candle, and we can see the light directly. An example of a non-luminous object would be a block. The only way we would see the block is if light bounced off it and we saw it with our eye. Again, the sun is a luminous object. It's a star, and it gives off its own light. A tree, the only way we see a tree is because light is reflected off the tree and our eye sees it. So this is non-luminous. Of course, the sun is luminous. There are different sources of light. There are natural sources like the sun, wood, bioluminescent organisms that make their own. And there are artificial sources like incandescent bulbs, fluorescent bulbs, phosphorescent, chemiluminescent. And so let's talk about some of those. Let's talk about incandescent light. Incandescent light is created by friction, basically. So what happens is electricity is run through a light bulb that is in almost a vacuum in here, and not quite, but almost a vacuum. And inside here is a gas that doesn't light on fire. Inert means that the gas isn't very reactive. So in a vacuum where there's very few particles and a tiny amount of gas, like helium, it will help create, when there is friction, brightness inside. So we use a filament, like a tungsten filament. That's a wire that can help slow the electrons down. And so electrons come up through the filament. They're slowed down by a tungsten wire, creating a lot of friction. That friction creates heat. The heat lights up the gas inside the bulb. And so that's how an incandescent light works. Incandescent lights, though, are very inefficient, which means it takes a lot of input energy and not much intended output. Intended output energy would be the light. How much light is created compared to how much energy you had to put in to make the light? Not very much light energy is made compared to the amount of wasted energy. If you ever touch these, you'll notice they get really hot. And that's not what we want. That's kind of wasted energy. Fluorescent lights, however, are produced by what we call electron bombardment of gases. Phosphors absorb photons that are created when mercury is zapped. Neon, same idea. And then LED lights are even more efficient. And what happens is, we talked about the photon effect again. So here's what happens. Electrons are passed through a tiny little opening, and they're brought up into a higher energy level, and then they fall back down. And that process, that photon effect, thanks to the help of what we call a diode, creates light. And it's super efficient. If you ever touch LED lights like this, like the new style Christmas lights, they don't get very hot because we're not using friction to light up something, which means not much heat is being generated. Neon lights are gas discharge lamps. They contain gas, such as neon, that release colored light when they're stimulated by electrons. Many street lights use a similar system. So this time around, again, there is no tungsten coil. Inside, there is no wire that heats up, that then heats the gas. Instead, what's happening is electrons are being excited within the neon gas. So neon, it's an atom. It has a nucleus, and then it has different energy levels for electrons. What's happening is we're using electricity to excite some of the electrons in the neon to a higher energy level, and then letting those fall back down, kind of like the photon effect. Let's look at a fluorescent lamp. So a fluorescent lamp is somewhere in between. It still has a filament, but that filament which causes the electrons to slow down, is not as hot, which makes fluorescent lamps more efficient. We have an argon gas in here, which is a gas that, again, is fairly inert. Inert means it won't blow up or explode very easily. And the gas is excited by this filament, and it kind of glows inside the tube, which is pressurized. So as electricity moves through the tube, it will collide with the gas inside, causing the gas to glow. Let's talk about chemiluminescence. So this is a chemical reaction. Some substances, when they undergo a chemical reaction, will give off light for a short period of time, and that's what glow sticks do. They're creating light through the rearrangement of atoms to make new substances that will flow and will glow for a little while. Here's the inside is a hydrogen peroxide, usually a solution, and then outside is organic substance with some fluorescent dye. And so we crack open the hydrogen peroxide, causing a chemical reaction to occur. And as long as there is enough reactants, the hydrogen peroxide and the phenyloxylate, it will keep glowing. But as soon as we run out of those chemicals, in other words, they collide and they mix to make products, that will run out. And eventually when it runs out, of course, the chemical reaction stops and there's no more light. We can cool this and slow the reaction down by putting it in the freezer to prolong this effect. Now, some biological organisms have chemicals very similar to a glow stick inside their bodies, and they can continue to manufacture these chemicals to glow in the dark. For example, fireflies in their abdomen can do this, and jellyfish also have genetic machinery to allow them to make their own chemical reactions within their cells. And unlike a glow stick, they can replenish these reactants so that they can continue to glow in the dark, and we don't have to put them in the freezer. Night vision goggles. So as you know, our eyes normally can't see in the dark. So how do night vision goggles work? Well, light is focused onto an image intensifier. Inside the intensifier, light energy releases a stream of particles which hit this special phosphor-coated screen. These glow green, and the person looking in the goggles can see a green image. So what's happening here is kind of the photon effect within the light vision goggles. Okay, even though it's dark out, objects still can emit radiation, okay, in the form of, for example, a heat signature, and night vision goggles will transmit or translate that radiation into us being able to see a bit of the light that, or converts it into light. The other thing I wanted to talk about is different light bulbs have different amounts of efficiency. We talked about how fluorescent bulbs are more efficient than incandescent, and LED bulbs are even more efficient. And so the LED bulbs, as I showed you before, are 93% efficient, which means they convert almost all their input energy into light. However, incandescent bulbs, the old style, are only about 15% efficient, which means the rest of it is heat. So the input versus the output. Well, we can calculate electricity costs based on this. So if the energy costs 11 cents per kilowatt hour, what would the person's electricity bill be? First in cents and then maybe in dollars. So a family uses 3,000 kilowatt hours in 2 months. So how much would that be if every hour it costs 11 cents every hour? So we got